Now we move to transformation of strain components. A transformation of strain component is one of the fundamental concepts in structure mechanics involving the change of strain components from one coordinate system to another. As we discussed, the strain components describe how an object deforms under the applied forces or loads. First of all, we will discuss the transformation of strain in a 2D space, and then afterwards we will discuss the transformation in the 3D space. The transformation of strain components between the coordinate system will be governed by a linear transformation that is similar to transformation of vectors. So we can see that there is an element having the stress components shown. The element is subjected to general state of plane stress. The reason we are calling it plane stress because we are ignoring the stresses in the third dimension. The normal stresses are assumed to be tensile and they elongate the element in x1 and x2 direction, whereas the shearing stresses distort the element through the shear strain gamma 1 2 as shown in this figure. Our coordinate axis, which is shown in purple, corresponds to the left corner of the element, or in other words, the coordinate axis has got an origin at the left corner of the element. The effect of these strains on any line element OA is shown in this figure. So we have the element which is OA, and that OA changes its angular position by a very small amount that we call beta, and also OA is elongated to OA dash. The movement of A to A dash is the vector sum of the axial elongations and the shear distortions. So horizontally, we say that A has moved by strain 1 into D1, where D1 is the horizontal dimension of this element. So this element is considered horizontally as D1 and vertically as D2. The reason strain 1 is multiplied with D1 is that we are trying to find out our deformation, which is equal to strain by the original length D1. Using the same logic, we can multiply the strain 2, which is in the x2 direction, to the original length D2. And the shear distortion gamma 1 2 can be multiplied with D2 in the x1 direction. So as we can see in this figure, the movement towards the left is gamma 1 2 times D2. In other words, this is just tangent theta is equal to perpendicular by base. Since we are dealing with very small distortion, so tangent theta is approximately taken equal to theta, and theta is gamma 1 2. That gamma 1 2 is multiplied with the base D2 to get the shear distortion, which is gamma 1 2 theta to D2. Please note that this movement of A is highly exaggerated to show how the vector sum may be resolved into two components, that is, one parallel and another one perpendicular to OA. The parallel component A double dash, A dash, represent the increase in length of OA, whereas the perpendicular component A double dash causes the change beta in the angular position of OA. The magnitude of A double dash A dash is found by projecting strain 1 D1, strain 2 D2 and gamma 1 2 D2 upon the direction OA. Thus, we get A double dash A dash is equal to strain 1 D1 cos theta. So, strain 1 D1 component along OA plus strain 2 D2 sine theta, which is this one, strain 2 D2, and its component along OA minus gamma 1 2 D2 cos theta. So gamma 1 2 D2 and its component along OA. Please note that instead of finding the components upon OA, we can also find it upon OA dash because the angle between OA and OA dash is very small. Please also note that along OA dash, strain 1 D1 is in the direction OA dash. Strain 2 D2 is again in the direction OA dash, whereas gamma 1 2 D2 is in the direction A dash O. That's why negative appears in the case of gamma 1 2 D2 cos theta. If we assume that OA is equal to ds, or in other words, the length of OA is equal to ds, divide a double dash a dash by ds, we will get the extension of OA, which is equal to strain 1 d1 cos theta by ds, strain 2 d2 sine theta by ds minus gamma 1 2 d2 cos theta by ds. Since d1 by ds is cos theta, d2 by ds is sine theta, and d2 by ds again is sine theta. Plugging the values, we get the extension of strain A in terms of strain 1, strain 2, and gamma 1, 2. The angular deviation beta can be found in a similar way. We have to divide a double dash by the length ds in order to determine our angular deviation. Projecting the movement of point A on the direction perpendicular to OA, we obtain AA double dash as strain 1 D1 sine theta minus strain 2 D2 cos theta minus gamma 1 2 D2 sine theta. Once this is found, again we can divide this whole expression by ds and plug the values of d1 by ds, d2 by ds. We get beta equal to strain 1 cos theta sine theta minus strain 2 sine theta cos theta minus gamma 1 2 sine square theta. As we know that the total change in the right angle between OA and its normal OB defines the shear strain for an element that is located theta from the x1, x2 axis. That is why we have to work out our angular deviation OB, which is at theta plus 90 degree. So plugging theta plus 90 degree in the beta equation, we get beta dash as minus sigma 1 sine theta cos theta minus strain 1 sine theta cos theta plus strain 2 sine theta cos theta minus gamma 1 2 cos square theta. Please note that beta and beta dash rotate in the opposite directions. So their absolute sum is equal to their algebraic difference. That's why the absolute sum is taken as beta minus beta dash. So, and that gives us strain 1 2 sine theta cos theta minus strain 2 2 sine theta cos theta plus gamma 1 2 cos square theta minus sine square theta. Thus, we have derived the axial strain and the shear strain for the 2D element. The axial strain, strain A in the direction of OA, and the shear strain gamma AB between the concurrent lines OA and OB can be rewritten by substituting the cos square thetas, sine square thetas,
and sine theta, cos theta in terms of two thetas. So strain A will become strain x plus strain y by 2 plus strain x minus strain y by 2 cos 2 theta minus half gamma xy sine 2 theta. Gamma AB on the other hand can be reduced in term of 2 theta to half gamma AB equal to strain x minus strain y by 2 into sine 2 theta plus half gamma xy cos 2 theta. It is important to remember that in the derivation of strain A and gamma AB, we have assumed tension strain as positive, clockwise shear strain as positive, and counterclockwise rotation theta as positive. It is important to note the similarity between the strain expressions and the stress expressions derived earlier. So the stress and strain expressions are analogous. The first term in the strain expression has got strains, and in the stress expression has got stresses. The second term has got one strain getting subtracted from the strain in the orthogonal direction, and in the stress expression the stress in one direction is getting subtracted from the orthogonal direction. The third term in both the strain and stresses is also analogous. The only difference is that the shear strain is halved, whereas in the stress expression, the shear stress is taken as full. Similarly, the shear strain expression and the shear stress expression are analogous. The first term in the shear strain expression has got strains involved, whereas in the shear stress expression has got stresses involved. The second term has got shear strain getting halved in the shear strain expression, and the shear stress is full in the second term of the shear expression. Due to this analogy, we can say that the principal strains, just like stresses, will give us as strain x plus strain y by 2 plus minus strain x minus strain y by 2 whole square plus gamma xy by 2 whole square, both terms under square root. And this is analogous to the stress expression derived earlier. Please note that in the stress expression we have got tau xy appearing full, whereas in the strain expression we have the shear strain getting halved. The direction of the principal plane can be determined from the equation tangent to theta p equal to gamma xy by strain x minus strain y. Now this expression is worked out by differentiating the strain equation with the strain expression with respect to theta and then equating that to zero. In a similar manner, we can derive our maximum in-plane shear strain as gamma max in plane by 2 equal to strain x minus strain y by 2 whole square plus gamma xy by 2 whole square, both terms under square root. The direction of the shear plane is equal to tangent to theta s equal to minus small brackets gamma x gamma y by gamma xy. It is important to remind ourselves that the principal strain expressions are derived from the principal plane directions. The principal plane directions, both for the axial strain and the shear strain, are derived by differentiating the axial strain and the shear strain expressions with respect to theta and then equating them to zero. After getting the principal directions, we can then plug back these expressions in the strain equations. And from there, we will get our principal strains. Let us try to understand how to use these expressions with an example. A differential element of material at a point is subjected to a state of plane strain. Strain x is equal to 500 into 10 raised to power minus 6. Strain y is equal to minus 300 into 10 raised to power minus 6. And gamma xy is equal to minus 200 into 10 raised to power minus 6, which tends to distort the element shown in figure. So we can see that this element, which is defined in xy coordinate system, is subject to an extension of 500 into 10 raised to power minus 6 in horizontal direction and a compression of minus 300 into 10 raised to power minus 6 in the y direction. Gamma xy is minus 200 into 10 raised to power minus 6. So this type of shear distortion will be as a result of shear stress in counterclockwise direction. As per our convention, axial strains in tensions are positive and shear strains produced by clockwise shear stresses is taken positive. In addition, the orientation in counterclockwise is taken positive. We are asked to determine the equivalent strains acting on an element of the material oriented at the point clockwise 30 degree from the original position. So orientation theta has to be negative as per our sign convention. So our expression derived earlier can be easily employed. We are given strain x, strain y, and gamma xy. Theta is 30 degree clockwise. So plugging the values in this expression, we get 500 plus minus 300 divided by 2 with a 10 raised to power minus 6 taken as a common factor in the first term. Then as per the second term, we have 500 minus 300 by 2 and again 10 raised to power minus 6 taken as a common factor times cos 2 times minus 30 degree plus 200 into 10 raised to power minus 6 by 2 times sine 2 times minus 30 degree. The third term has become positive because gamma xy as per our sign convention is negative, and that negative with the negative appearing in the expression becomes positive. Thus, solving this expression, we will get strain x prime is equal to 213 into 10 raised to power minus 6. Now using the shear strain expression as strain x minus strain y by 2 times sine 2 theta plus gamma xy by 2 cos 2 theta. So putting the values 500 minus 300 by 2, 10 raised to power minus 6 taken as a common factor times sine 2 times minus 30 plus minus 200 into 10 raised to power minus 6 by 2 into cos 2 times minus 30. And we get gamma x prime y prime equal to minus 793 into 10 raised to power minus 6. Negative strain indicates that this shear strain is produced by a shear which is acting counterclockwise. In order to get another strain which is orthogonal to this strain, we can add 90° to our required orientation, which is 30°. Thus, 90 minus 30 will become 60°. Now, using the same expression, but this time theta equal to plus 60°. So we can imagine that strain x prime is in the direction minus 30° with respect to x-axis, then strain y prime will be counterclockwise 60° with the x-axis. So again 500 plus minus 300 by 2 with 10 raised to power minus 6 taken as common factor in the first expression, then 500 minus 300 by 2 times 10 raised to power minus 6 times cos 2 times 60° plus 200 into 10 raised to power minus 6 by 2 sine 2 times 60°, and we will get strain y bar equal to minus 13.4 into 10 raised to power minus 6. Thus the final orientation of our element comes out to be as shown in this figure. Strain x is positive as per our workout. Gamma x prime y prime is negative, hence we have this distortion due to counterclockwise shear. Strain y, on the other hand, is negative as shown in this figure, and that agrees with whatever we have derived. We will now try to determine plane strain transformation using Mohr circle. As we discussed earlier that the equation of plane strain transformation are mathematically similar to the equation of plane stress transformation. Therefore, we can solve the problems involving plane strain transformation using Mohr circle. In the case of plane stress problems, we determine the radii and the center of the circle using the stress equation and the shear equation. The stress and the shear expressions were derived in terms of 2 theta earlier. The main idea was to bring the terms without the thetas to the left and keeping the terms with thetas to the right. Thus, in the case of stress expression, the first term was brought to the left, and in the case of shear expression, we had the terms involving thetas left at the right hand side of the equation. After squaring and adding, we managed to eliminate the terms involving thetas, and we were left with an expression without any theta. This expression was in the form of equation of a circle. Hence, from this equation, we determined our radius and the center of the circle. We can do the same exercise in the case of plane strain problem. So the expression involving plane strain transformation are mathematically similar to the expressions of the plane stress problem. Hence, bringing the terms without thetas to the left, axial strain and the shear strain expressions, and then squaring and adding will give us the equation of a circle. We can see from this equation of circle that the center of this circle is on epsilon axis at a point C, having vertical coordinate equal to 0. The radius of this circle is epsilon x minus epsilon y by 2 whole square plus gamma xy by 2 whole square, both terms under square root. In accordance with our equation of circle, we have the center C located at a distance epsilon x plus epsilon y by 2 from the vertical axis. The circle is located on the horizontal axis. The coordinate system of the Mohr circle is arranged in such a way that epsilon represents the abscissa and the shear strain gamma by 2 represents the ordinate. The circle is drawn in accordance with our sign convention, which is that axial strains are positive, shear strain caused by shear stresses in clockwise direction are positive, and the orientation of the element in counterclockwise is positive. In the Mohr circle, point A is plotted as a reference point having epsilon x and minus gamma xy by 2. This reference point will represent the case for which the reference x bar axis coincide with the x axis, and hence theta will be equal to 0. Once we locate point A on the Mohr circle, we can easily join it with point C and hence get the radius of the Mohr circle. Once we find out our radius of the Mohr circle, we can sketch the circle. As we said, the orientation of the strain element with respect to the given point is considered as the reference point, and theta corresponding to that point is equal to 0. We can easily determine the principal strains. As we can see, the principal strains will be at point B and D, where the shear strains are 0. Point BD is located at an angle to theta P1 from our reference axis CA. So if we rotate our element counterclockwise by an angle to theta P1, we will get that orientation where our principal strains are located. The angle to theta P1 can be determined using trigonometry. In our current case, the principal strains are both positive, hence they show elongation. It is important to appreciate that the angle between the radii to the selected point on the Mohr circle is twice the angle between the normals to the actual planes represented by these points. The rotational sense of this angle correspond to the rotational sense of the actual angle between the normal to the planes. So for example, if an axis is actually at a counterclockwise angle theta p1 from the x-axis, Then on the Mohr circle, it is laid off at a counterclockwise angle 2 theta p1 from the x-axis. So this angle 2 theta p1 on the Mohr circle is in reality theta p1 in counterclockwise direction. In a similar manner, we can find out the plane where our shear is maximum. In the current case, from our reference point CA, the shear plane is oriented at 2 theta s1 in clockwise direction. So from x-axis, the actual angle between the normals to the plane is theta s1 in clockwise direction. From the distortion of this element, we can see that the dotted line shows the distortion of this element, and it can be realized that this distortion is caused by shear stress in counterclockwise direction. Please note that our reference shear strain on the Mohr circle is, is in negative ordinate direction. Similarly, we can determine normal and shear strain components oriented at any angle theta corresponding to our reference strain element. We can determine all the unknowns using trigonometry. We can now discuss an example to understand the application of Mohr circle. The state of plane strain at a point is represented by the components epsilon x equal to 250 into 10 raised to power minus 6, epsilon y equal to minus 150 10 raised to power minus 6, and gamma xy equal to minus 120 10 raised to power minus 6. Determine the principal strains and the orientation of the element. So the first step is to establish a coordinate system such that abscissa represents normal strain with positive to the right side, and the ordinate represents half the value of shear strain with gamma by 2 positive upward. The given state of plane strain has epsilon x in the positive direction, hence tension, epsilon y in negative direction, hence epsilon x positive, hence extension, epsilon y in negative direction, hence shortening, and gamma xy again negative, hence caused by shear stress in counterclockwise direction. So our state of plane strain will come below the epsilon axis. The center C of the Mohr circle on the epsilon axis is located at epsilon x plus epsilon y by 2 from the origin. Hence, epsilon x, which is 250, plus minus 150 by 2 with 10 raised to power minus 6 taken as a common factor, we get the center of the circle C equal to 15 to 10 raised to power minus 6. Gamma xy by 2 will come out to be 16 to 10 raised to power minus 6 and in negative direction. Hence, we would have coordinates of A equal to 15 to 10 raised to power minus 6, comma, minus 16 to 10 raised to power minus 6. We can use Pythagoras theorem to determine the radius, and that is equal to 250 minus 50 whole square plus 60 whole square, both terms under square root. And from that, we will get 208.8 into 10 raised to power minus 6. So we can connect A with C and determine our radius R. Having known the center of the circle and the radius of the circle, we can now easily sketch the Mohr circle. We are asked to determine the principal strains and the orientation of the element. As we can see that from our given state of strain, the principal axis is located at an orientation 2 theta p1 counterclockwise from our reference line AC on the Mohr circle. 2 theta p1 can be determined using trigonometry. So tangent 2 theta p1 is equal to 60 by 250 minus 50, and hence we would get theta p1 equal to 8.35 degree counterclockwise. We can determine the principal strains P and D using trigonometry. Thus, sigma 1 will be equal to 50 plus the radius 208.8, and we will get 259 into 10 raised to power minus 6. Epsilon 2 will be equal to 50 minus 208.8 into 10 raised to power minus 6, and that will come out to be minus 159 10 raised to power minus 6. In other words, DC is 208.8. 208.8 minus 50 will give us 159 into 10 raised to power minus 6, and that has to be in negative direction because the second principal strain is in the negative direction. After this, we can draw our principal strain state. The principal strain state is oriented at 8.35 degree from our reference x-axis in counterclockwise direction. Strain 1 is getting extended as it's positive, and strain 2 is causing shortening since it is negative.